Okay, example 17, we start to get into the composition of functions, and that's really the combining of functions. And this takes a lot of the concepts that we've been learning and starts to bring them together. But before we get into that, let's start with an example that's a little bit more in line with what we know about functions, with our traditional understanding of functions. So here we have f of x is x squared. So that function, if we have x over here and we have f of x over here, 1, 2, 3, 4 on down. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16 on down. And then we have x and g of x. So g of x is just x minus 1. So again, if we have 1, 2, 3, that's going to be 0, 1, 2, and go on down. Right? So those are two functions. If we say f of, this is supposed to be, kind of a little special O symbol there, f of g, what we mean is f of g of x. That is, the output of g of x becomes the input of f of x. So in that case, if we have x and then FOG 1, 2, 3, well, we know that g of 1 is 0. Well, we don't have it written here, but 0 squared is 0, right? G of 2 is 1, so g of 2 is 1, which will get us 1 up here, so that will be 1. As for 3, that gets us 2, which we plug in over here, and we get 4, and on down. So when we composite two functions, we take the output of one function, make it the input of another function, which when we're dealing with integers like this, it's pretty straightforward. It gets a little bit more complicated once we start getting into our traditional definitions of functions, and that's what this example is all about. All right, let's put this into a more solid example. Let's define a new function f, which is equal to, we're going to give the two-line notation here, lowercase p to uppercase p, q to uppercase r, r to uppercase t, and s to uppercase u. So that's our function f. And we don't need to worry about order because we've defined our own order in that top row for the domain. Let's define g as uppercase P to 1, uppercase Q to 3, uppercase R to 5. Okay, so we have defined f and g here. Now we need to define g of f. By the way, in your book, they tend to leave off the O, that of symbol, either way. And we're going to, and that, we don't need to define that. So first we have to take a look at f. So f maps, lowercase p maps to uppercase p, which over here maps to 1. Q maps to R, which maps down here to 5. R to T to 4, and S to U to 6. So this composite function, g of f, looks like this. Now, let's suppose we also had a method h. Can I do h of g of f? Yes. Can I do h of g of f? Yes, I can. Are they the same? They are. They are equivalent. Due to the commutative law of composition. I'm not going to prove the commutative law of composition. Just know, just like with our other commutative law, the parentheses don't matter. When you're doing compositions, you can drop them entirely. Now, order does matter, right? As we can see, g of f is not the same as f of g. They're very different. but once they're in that order, the parentheses do not matter. Okay, continuing this example, they on the bottom of SF20, they essentially start a brand new statement without saying, hey, I'm starting something new here. And then they have a short paragraph, which is really something very profound, but they don't explain it as profound. So they say, suppose you have a set A, and you have F and G are permutations on set A. Remember what we mean by a permutation. So let's say that set A, in our example here, is going to be 1, 2, 3, right? We'll say that F is 1, 2, 3, right? So that is a permutation. And G is, so each of those sets is a permutation. If it's a permutation, that means it is a bijection. So it is both a surjection, right? And we see every member of the range represented in the image here, right? Every member of the range is in the image there. Every member of the range is in the image there. And each member is only there once. It's an injection. Each one is only there once. So because it's a bijection and because the domain and the range are both the same set, we call those a permutation. Also, because it is a bijection and because it's a permutation, then we can have an inverse of F. What's the inverse of F going to be? Well, in the inverse of F, 1 maps to 3, 2 maps to 1, and 3 maps to 2. So that is F inverse. If you do F, and F of F inverse is always F, right? Now, here's the question then. What is F of G? In this case, F of G is going to be, so 1, 2, 3. So 1 goes to 2, and over here 2 goes to 2. 2 goes to 3, and over here 3 goes to 1. And then 3 goes to 1, and there 1 goes to 3. So it's 2, 1, 3 is F of G. Now what do you notice about F O G? 1, it is a mapping from set A to set A. 2, it's a bijection. So F O G is also a permutation, right? And it's a permutation such that the inverse of F of G equals G of F. I'll let you do that one yourself to prove that to yourself. But that's an interesting property when we have composites that are permutations. That if each is a permutation of the same set, then their composite is also a permutation of that set. And that is used a whole lot in cryptography to make more complicated encryption schemes. Okay, there's one little last paragraph in example 17 where basically they're just saying that, if you have F of F of F of F, it doesn't matter which order you do the composition in, which is the associative law that we talked about before. That last paragraph I'm not super concerned with. That's everything you need to know from example 17. If you have any questions, ask them in the forum below.